All right, welcome back, everyone. If you're on this AI tech path with us, and especially if you're following along with Stanford's CS224R course, you know that Lecture 4 drops this really clever idea. So today, we're going to dive into that core concept, how we can teach an AI to learn in a much smarter, more nuanced way, moving way beyond just simple trial and error. So, let's get right to it. The big question we're trying to answer is this: how does an AI actually learn from its successes and failures, but in a way that's, well, smarter? I mean, it's pretty easy to just reward a win and punish a loss. But what about all those little, crucial decisions that happen along the way? That's the tricky part, and that's what we're going to unpack. Here's the plan. First, we're going to look at a pretty basic learning method called policy gradients and see exactly why it just doesn't cut it. Then, we'll introduce some much smarter tools for judging actions. After that, we'll meet the incredible actor-critic duo, figure out how we train them, and finally, we'll put the whole thing together into one really powerful learning algorithm.
Okay, so, first things first. To really appreciate the smart new way of doing things, you gotta understand the old way and its biggest, most glaring problem. So, let's dive into policy gradients.
You can think of policy gradients like this. An AI plays a whole game from start to finish. And at the very end, it just looks at the final score. That's it. If it won, it basically thinks, awesome, everything I just did must have been brilliant. I'm going to try to do all of that again. And if it lost, it's like, well, that was a disaster. I'm going to avoid everything I just did. It's simple, for sure. But as you're about to see, it's maybe a little too simple. And this is where that simple approach just completely falls apart. Imagine an AI learning to walk. It takes one perfect, well-balanced step forward, a fantastic move. But then it messes up the very next one and faceplants. The final outcome is negative, right? A pure policy gradient algorithm would look at that whole sequence and punish every single action, including that amazing first step. It just doesn't have the nuance to see the little bit of good hidden inside a bad outcome. So you end up with a few big problems. The feedback the AI gets is incredibly noisy, what we call high variance. One lucky shot or one clumsy mistake can color the entire experience. It's also super inefficient with its data, because it's throwing away perfectly good moves just because they were part of a losing game. And it really struggles when rewards are rare. Like, it might never figure out that folding the sleeves of a jacket is a good step towards the final goal of folding the whole thing.
Okay, so if just looking at the final score is too blunt an instrument, we need better tools, right? We need a smarter way to judge each step of the journey, not just the destination. And this is where things start to get really cool.
So, tool number one is something called the value function, or V of S. Think of it as the AI asking itself a simple question. Putting aside my next move, just how good is my current situation? Am I in a good spot? It's all about estimating the potential of the state you're in right now, assuming you keep playing your normal strategy. Then we have the Q function, which gets even more specific. It asks, okay, I'm in this state, but what if I take this specific action right now? It tries to predict the future reward if you commit to one particular move. It's not just about how good the state is, it's about how good a move from that state is. And all of that leads us to the real game changer, the advantage function. This is the key. It just asks a simple but powerful question. How much better, or worse, is taking this action compared to my average, normal move from this state? It's literally just the Q value minus the V value. It tells us if a specific move gives us an actual advantage over our usual habits. This drummer analogy from the lecture just nails it. Let's say your goal is to learn drums, but your default policy, your habit, is to just go sit on the beach. Well, the value of that state, V of S, is 0. You're not getting any closer to your goal. Now what about your actions? Sitting on the beach gets you nowhere. Watching TV also gets you nowhere. But practicing the drums? That action has a positive Q value. It could actually lead to success. And because it's better than your average do-nothing policy, its advantage, it's positive. It's the only move that's actually better than what you'd normally do. So we have these new, smarter tools. How do we actually put them to work? Well, we build a team. And this is where we meet the actor-critic model. Think of it like this awesome duo, right? You've got the actor, that's the policy, the part of the AI that's actually out there doing stuff, making moves. It's the performer on stage. Then you've got the critic. That's the value function, sitting in the audience with a scorecard, watching everything the actor does and giving it feedback. The actor tries things out, and the critic chimes in with,
hey, that move was surprisingly good, or, that was actually worse than I expected from you.
And just like that, the whole goal of learning completely flips on its head. We're no longer just trying to reinforce everything that led to some distant win. Instead, the actor's new job is to do more of the actions that the critic identifies as having a high advantage. We're learning from smarter, more targeted, and more immediate feedback.
Okay, but wait a second. This all sounds great, but it brings up a really important question. If our whole system depends on having a good critic, how in the world do we make sure the critic actually knows what it's talking about? How do we train a good judge?
Well, one way is the Monte Carlo method, and this is going to sound a little familiar. Here, the critic just waits until the entire game is over, looks at the real, final score, and then uses that ground truth to update its predictions about what happened earlier. Now, this is great because it's unbiased. It's based on the true result, but it's also super noisy or high variance for all the same reasons we talked about before.
But then there's this other, really clever way called bootstrapping, or TD learning. Instead of waiting till the end, the critic takes just one step, looks at the immediate reward it got, and then asks its own past self for a guess about how good the next state is. It's pulling itself up by its own bootstraps. It's way less noisy, but it can be biased because it's learning from its own, possibly flawed, estimates. And this example is just perfect for showing you why this matters so much. First, look at the blue state. From there, the agent has seen paths that end in both a +1 and a -1 reward. So both methods average that out and correctly figure out its value is 0. No problem. But now look at the pink state. Let's say, just by chance, the only time we've been there, we took a path that led to a -1. Monte Carlo only sees that one history, so it thinks the pink state is terrible. But bootstrapping is smarter. It takes one step, lands in the blue state, and asks, hey, what's your value? The blue state says, I'm a 0. So bootstrapping updates the pink state's value to be 0. It's effectively sharing information from that other path, leading to a way better and faster estimate.
All right, we have all the ingredients, we've got our actor, we've got our critic, and we know how to train them. Let's put it all together and see what this beautiful learning algorithm actually looks like in action.
It really boils down to this elegant three-step dance. Step 1, the actor goes out and acts, playing the game and collecting experience. Step 2, we take all that new experience and use it to train our critic, making a better, smarter judge. And step 3, we use the critic's newly improved advantage scores to update and improve the actor. And then this cycle just repeats. The better actor collects better data, which makes a better critic, which makes an even better actor. They both get smarter together.
And just so you know, this is not just some neat academic theory on a slide. This is a huge deal. This fundamental actor-critic framework is the engine that powers many of today's most advanced AI systems, from the large language models you hear about every day to incredibly complex humanoid robots. This is the real deal.
Which kind of leaves us with this one last fascinating thought to chew on. If an AI has this internal feedback loop, one part that acts and another part that evaluates those actions based on its own learned experience, are we kind of seeing the emergence of a computational form of intuition? A system that isn't just following a set of hard-coded rules, but is actually developing its own internal sense of what makes a good move? It's a pretty wild question to think about.